Hello everyone, I'm Xinchen Liu from Zhejiang University in China. Today I will report our paper, Physically Based Modeling and Rendering of Avalanches. The authors are Xinchen Liu, Yi Chen, Haitong Zhang, Yunhong Zhou, Zhangye Wang, and Qunshen Peng. And I'm today's speaker, Xinchen Liu. My present outline are as follows. Introduction, related works, physically based modeling of avalanches based on geodynamics, level set-based interaction modeling of avalanches, realistic rendering of large-scale avalanche scenes, results and discussion, and finally conclusions and future work. Firstly, it is introduction. As we all know, avalanche is a natural disaster. It may cause great disasters to human life and property. It is also a danger for skiers and climbers. The simulation of avalanche can be found in prevention, rescue, game design, film, and TV. We present a new physically based modeling and rendering algorithm for dynamic avalanche in this paper. And this is our main contributions. Firstly, it is a novel algorithm in computer graphics to physically model and render large-scale dynamic flow of avalanche. And we proposed a new snowflow model based on viscoplastic materials. It fully considers the main internal force mechanisms. Then we put forward a lead set-based model to efficiently simulate the interaction between snowflow and the surrounding obstacles. And finally, we present an aerodynamic-based particle drag force model to generate snowfall effect. Here are some related works to introduce. In geology areas, many studies focus on the numeric simulation of their dynamic processes based on safety models. And early snow-related computer graphics work focuses on simulating static snow scenes and some weak dynamic snow scenes. Recently, John introduced the MPM method to avalanche simulation and the snow stability analysis. They achieved realistic results but failed to present the snowfall effect in avalanche. And our work is to propose a novel physically based modeling and rendering algorithm. We firstly adopt Bingham plastic model to get motion of snow flow, and we use the level set algorithm to do the fluid-solid collision detection. And the aerodynamic drag force model helps us to produce the snowfall effect. And finally, we render the different kinds of avalanche scenes. Physical modeling of avalanche based on geodynamics. In geology, avalanche occurs when the snow layer cohesive force and friction cannot resist external forces such as gravity. Figure 1 is the illustration of an avalanche triggering state of a snow layer. The avalanche can be caused by natural forces and human activity. Our algorithm is under position-based dynamics framework. We solve particle positions and do corrections under different constraints. This is our algorithm overview. The step 1 is initial particle attribute. Step 2 is update particle velocity. Step 3 is damping particle velocity. Step 4 is predict particle position. Step 5 is solve elastic constraints. Step 6 is collision detection and static friction. And step 7 is update position and velocity. And here we need to solve the plastic constraints. We adopt the Bingham model, make it plastic modeled by shear rate and yield shear rate. As shown in the picture, the higher the criterion shear rate is, the harder it would be deformed. The relationship between shear strain rate and shear stress of Bingham model is shown in the picture. When the shearing stress is greater than the critical shearing stress, plastic flow occurs. When the shear stress value is less than the yield stress, it shows the property of no deformation. And when the shear stress is greater than the yield stress, plastic flow and substantial deformation occurs. After the plastic calculation, we do the cohesion and friction calculation. We modeled kinetic friction and cohesion by combining the Bingham model with the Morrow-Coulomb equation. And from the results, we can see that the bigger cohesion parameter value is, the stronger the particles' tendency to stick together. And we achieve the static friction separately from kinetic friction by referring to the method of Maclaurin. By adjusting the static friction parameter μs, piles of snow with different angles formed when the particles turn to stationary state under the scene of snow falling to the ground. Next is level set-based interaction modeling of avalanches. We use sine distance function to solve the surface normal and tangent. According to Morrow-Coulomb first law, there exists static friction between particles and object surface. Their relative velocity will decrease due to the friction. And Figure 7 shows collision detection of snow particles and complex surface objects by using SDF function. After simulation, we need to realistically render large-scale avalanche scene. We consider the air dragon force as an external force and implement it to achieve snow fog effect. We simulate dragon force in single-phase flow framework, and we introduce a more accurate and easily controlled shape function and add it to Gauss's generalized model to simulate the snow particles dragon force with different snow particle shapes. And Figure 8 shows that. And this is our rendering and accelerating strategy. We use weighted method to generate the initial volume object required for snow and fog calculation. Firstly, the particle velocity information is weighted by a Gauss kernel, and then the particle attributes are transferred to the grid. And finally, the grid data are transmitted to the corresponding Houdini server to obtain snow and fog data. Now let's go to the results. Here is the sequence of pictures of a weight avalanche. The feature of the weight avalanche includes the appearance of snow layer fracture. And this is the sequence of pictures of a dry avalanche. The snow fog effect is rendered based on the proposed aerodynamic dragon force model, and we can see the snow fog. And this is the comparison of our simulation results about the whole scene, zoomed results, and the real scene. By compare them, we can see that the visual effect of our simulation and rendered results of the avalanche scene is quite satisfactory. And let me show you some data. Table 1 shows the comparison of scene parameters and simulation time in different sceneries in this article. All the simulation experiments and results are run in Intel Core i7 7700 CPU and NVIDIA GTX 1080 Ti GPU. The time step of all the scenes is set to 0.001 seconds. And Table 2 is the comparison of the computing efficiency between computing strategies with and without GPU. The speed-up rate reaches 50.5 times. Now let's see a movie about the avalanches. We present a physically based method to simulate the dynamic process of snow avalanche, and this is the dry and wet avalanche sequence. And here are our main contributions. We can see the different results with different criterion shear rate. The bigger the criterion shear rate is, the harder it would be deformed. And the bigger the cohesion is, the particles will stick together. And this is the different results with different static friction parameter values. And we can see different sliding down effect of snow flow with different snow particle shape parameter values. Here F shape equals to 0 and equals to 50. And F shape equals to 100. And this is the collision detector effect. And we can see the weight avalanche sequence from initial state to end state. And this is a snow fracture effect of a weight avalanche. We can see that clearly in zoom-in view. And here is the whole weight avalanche dynamic scene. We can see the fracture. And it is the dry avalanche sequence from initial state to end state. We can compare it with real photos, and we can see the results are really realistic and satisfactory. And this is a whole dry dynamic avalanche scene. You can see the snow rapidly slow down and the snowfall comes to us. Okay, that's the end of the demo. And finally, let me introduce our conclusions and future work. We present a new physically based modeling and rendering algorithm under PPD calculation framework to simulate the dynamic process of avalanche. And compared with the real photos of avalanche, our simulation and rendered results are quite satisfactory. To realistically simulate avalanche's dynamic characteristics, Bingham's plastic model from geodynamics is introduced to model the snowflow motion in avalanches, and the Dragonforce model makes us to generate snowfall effect. Our future work will include the more accurate analysis of slope stability in avalanches to generate more realistic dynamic crack propagation effect of avalanche scenes. That's all. Thank you.